In the last class, we have introduced some integrals. From the standard Riemann integral, we have extended this to define Riemann Stieljes integral and then Lebesgue Stieljes integral. So, these are all generalizations of Riemann integral, where Riemann integral of a function is defined with respect to x, and here in Riemann Stieljes integral, we usually integrate a function with respect to another function. Usually this function is usually taken to be distribution function, that means it has some connection with the probability theory. So, today we will discuss in detail some of the important properties of Riemann Stieljes integrals, and also we will discuss a new thing where usually we have the idea of a sequence of real numbers. Similarly, we can also define, or we have some idea about the sequence of functions, sequence of real valued functions to be more precise. So, what happens, or is there any relationship between this, or is there any connection between this sequence of functions, between the limits of the sequence of functions, and can we define some kind of integrals with respect to this sequence of functions and any kind of convergence, whether we can think like that. So, today's topic is mostly related to some important properties of Riemann Stieljes integrals and some connection or relation or some kind of transition between these integrals and the sequence of functions and their limits and so on. So, let us just have a quick recap of what is the meaning of Riemann Stieljes integral. Suppose we have a distribution function capital F x, g x is a continuous function in the interval, let us take closed interval a to b, and we consider a partition P of a b, that means by inserting n plus 1 points within this interval. So, a equals to x naught less than equals to x 1 and so on less than equals to x n equals to b, and we define the Riemann Stieljes sum as summation I equals to 1 to n g of xi I into capital F of x I minus capital F of x I minus 1, where xi I is an arbitrary point within the ith sub interval. That means, if we take the ith interval as xi minus 1 to xi, then xi I is a point lying in that interval. Now, we consider the limit of this sum, which is limit of n, limit as n goes to infinity, that means number of points in this partition goes to infinity of this RS Riemann Stieljes sum. If this limit exists, then we say that this limit is nothing but the Riemann Stieljes integral and is denoted by a to b g x d f x. That means, it is clear that here we are basically integrating g x with respect to the function capital F x, where capital F x is a distribution function and g x is a continuous function. Now, the question is it possible, here we have taken the limits to a to b which are finite. Now, the question is, can we extend these limits to minus infinity to infinity? Answer is yes, but there are some conditions. So, we can easily extend this RS integral to infinite intervals, but in that case g x should be integrable over a b with respect to f x, where a and b are any number on the real line. So, now this Riemann Stieljes sum goes toward the limit equals to minus infinity to infinity g x into d f x. This is denoted like this, whenever maximum of the length of the ith sub interval goes to 0 over I, goes to 0 as n goes to infinity, and naturally a goes to minus infinity and b goes to infinity. So, under this condition we can easily extend the RS integral to include the infinite interval. So, next question is, as we know there are some properties of standard Riemann integral. So, we should discuss some properties similar to that of the Riemann Stieljes integral, and these are very standard properties. So, integration a to b g 1 x plus g 2 x d f x you can split this in integral of sum as the sum of integrals like a to b g1x dfx plus a to b g2x dfx. Similarly, we can think of integral a to b gx d of f1x plus f2x equals to a to b gx df1x plus integral a to b gx df2x. We can also split the interval of integration, as for example, in this case a to b gx dfx equals to a to c gx dfx plus c to b gx dfx, where c is any point within the interval a to b. Another interesting property is that if gx is Riemann Stieljes integrable or RS integrable and g is bounded, that means lies between bounded by small m and capital M, and phi is a continuous function defined on small m to capital M on this closed interval, then if we define another function h x as phi of g x, then this g x this h x is also Riemann Stieljes integrable or RS integrable on A B. Now, I will just give you this outline of the proof, because the proof is very simple and straightforward. Just recall the definition of RS integral, which is nothing but the limit of this sum g xi I f of x I minus f of x minus 1 x I minus 1, where xi I is the arbitrary point in the ith subinterval. And if we apply to each of this integral this limit, the proof follows immediately, and this one we need the condition of continuity of phi. So, I just leave this proof, the detailed proof. It will be easy, just write it down and you will get the proof. Next one is, as I mentioned, we will be discussing two important theorems, and the first one is Helly's theorem, which is related to the sequence of functions. Suppose a non-decreasing in x sequence of functions f n x converges to f x, and g x is everywhere continuous and a and b are continuity points of f x. That means, a and b are 2 points where capital F x is strictly continuous. Then limit n goes to infinity a to b g x d f n x. So, remember, this is the sequence of functions. We are introducing this sequence of functions here, with respect to which we are going to find out the integral of this function g x. Now, this limit exists and it is equals to a to b g x d f x. So, this is the famous Helly's theorem, and I will just discuss this Helly's theorem using an example. Suppose capital F n x is something x to the power 3 plus 2 by root n, which goes or converges to x to the power 3, and g x is set at x equals to x, g x is taken as x square for x lies between 0 and 1. Then as n goes to infinity, so we should expect that this will hold. So, Helly's theorem states that integral of this quantity limit of that n goes to infinity should converge to this. Now, let us calculate this integration of g x with respect to f n x, that means integration of x square with respect to d of f n x, that is d of x to the power 3 plus 2 by root n within the range 0 to 1. And simple integration will show that this value is 3 plus 2 by root n divided by 5 plus 2 by root n. And this goes to, as n goes to infinity, these two quantities goes to 0. So, this entire quantity goes to 3 by 5, and it is clearly seen that 3 by 5 is nothing but the integral of x square with respect to x cube, which is nothing but d of f x. So, Helly's theorem is satisfied, and we can use this result of Helly's theorem, to get the limit of this integral with respect to this function. I am not going to give you the detailed proof, but rather prefer to discuss this example using some diagrams. So, as we know, integration means this is basically that the area under a curve. So, here this means that this is the area under the curve of x square when in the horizontal axis we plot f n x. Similarly, this would be the area of x square in the with respect to the axis which is given in terms of x cube, which is capital F x. So, if we can show that as n goes to infinity, this area under this curve, this integral converges to the area under this with respect to this x cube, then we are done. So, this is our f n x, f x equals to x cube, g x is x square, a equals to 0 and b equals to 1. So, we plot g x in the vertical axis and f n x or f x in the horizontal axis. First, let us consider this graph. So, for n equals to 1, if we calculate the shed the area under the curve g x with respect to f n x. So, f n x is in the horizontal line, horizontal axis, and g x is in the vertical axis. So, if we plot, this is the curve and the red shaded area is nothing but the area under this curve, and this black curve gives us the integral g x with respect to f x. So, this shaded area shaded by black color is nothing but the area of the curve g x under capital F x. So, you see when n equals to 1, there is a substantial difference between these two areas, and this part is not covered by the black shade. So, when n equals to 3, if we look at the same picture, if we plot the same graph, we see that this area that is only red, but not shaded with black, is being reduced compared to when n equals to 1. That means, it starts approaching towards this black area. When n equals to 20, this is very prominent that this red area, only red area, is again much less compared to this one. So, it means that this red, only red area, which is not also shaded by black one, actually starts converging towards the black curve or the black region, and when n equals to 200, it almost converges to the black. So, if you increase, you will not be able to distinguish between these two areas. So, that gives us a nice pictorial representation of this convergence of rather the demonstration of Haley's theorem. So, outline of the proof I will just give you. So, capital F n x is a non-decreasing function for all n, and again we partition this interval, then consider the integration of g x d f x. Now, we can easily write this integral within the sub interval g x d f x and take the sum over all such intervals, and we forcefully add and subtract this g x I. So, g x I d f x I we subtract and then we add. So, if we add this, consider the term with the addition of g x I, that means, it is summation integral g x I into d f x. Now, g x I is a constant with respect to x. So, g x I comes outside and d f x becomes just f of x I plus 1 minus f x I, and this part actually is very small, because this is with respect to f x. As k goes to infinity, this is very close to 0. So, let us call this is less than theta 1 into epsilon by 3, and let us put this as it is. So, let us suppose equation 1. Now, consider exactly the same thing, but with respect to f n x, and do the same trick here. We will get almost the same expression, except that capital F is replaced by capital F n. Now, since capital F n x goes to capital F x at all continuity points of f, that is our assumption, then naturally if we subtract 1 from 2, this part corresponding to this part goes to 0. So, that also this 2 minus 1, whatever be the expression, the entire quantity, the absolute difference of this 1 and 2 is less than epsilon when n goes to infinity or n is large. So, just take n goes to infinity, the proof follows. So, this is just an outline of a proof, just write it down, this splitting of introducing g x I and then subtract g x I, and you will get the detailed proof. Next one is Haley-Bray theorem. So, what is the possible extension that actually leads us to Hilbert theorem? That is a very good question. And one natural extension should be that whether we can extend the limit to infinity, minus infinity and infinity. So, there are some conditions. So, if g x is continuous, f n x converges to f x for every continuity point of f x, and for every epsilon greater than 0, we can find some number capital A such that minus infinity to minus a mod of g x d f n x plus a to infinity mod of g x d f n x, it is less than epsilon. That means that, so actually if you recall the Hillis theorem, this part was not there, this C part. So, it is enough to have g x and f n x goes to f x when we consider an interval a to b. But when we want to extend this entire integral or entire Hilbert theorem to the infinite, to consider the entire real line, that is minus infinity to infinity, that means that there should be a very negligible contribution towards the two ends or two tails of the real line. That means, if we consider this integral, suppose a is a very large number. So, a to infinity, this has almost no contribution, and also this quantity which is very close to minus infinity, the range is very close to minus infinity. That means, a is a large positive quantity. So, minus infinity to minus negatively very high quantity, this entire contribution of this integral within this range is negligible. So, whenever these two tail portions of the integrals with respect to f n x is negligible, then obviously we can assume that they do not have any contribution. So, we can immediately get this theorem. So, this is a very intuitive idea of this, how the proof goes basically. So, if we consider, so this condition is essential to extend it to minus infinity to infinity, that means to extend a to b to minus infinity to infinity in the Hillis theorem, which is known as Hilbert theorem. So, then under these three conditions we have limit n goes to infinity, minus infinity to infinity integral of g x d f n x is equals to minus infinity to infinity g x d f x. So, this gives us a more flexible way to consider the integrals of a function over the entire real line. So, this might be a very important jump from Hillis theorem or what is stated in Hillis theorem to what is stated in Hilbert theorem. So, this actually encompasses any finite interval as well as any infinite the infinite interval, that is the entire real line, provided these conditions should satisfy. So, today we have discussed some properties of Riemann Stieljes integral that is very similar to the properties of standard integrals or standard Riemann integral that we already knew. We also discussed two theorems, one is Hillis theorem, another is Hilbert theorem, and they are related with the integral of sequence of functions, rather the Riemann Stieljes integral of sequence of functions with respect to another function, and what happens when n goes to infinity. That means, what happens when the integral to the integral when n goes to infinity. So, obviously, this limit should exist, and we have seen that it actually exists only under some conditions, but usually these conditions are more or less common, and most of the standard functions with which we usually deal with, they already satisfy all these conditions. So, in many real life applications, we can use very frequently this Hillis theorem and Hilbert theorem to get some desired and interesting results. And we will see some of the direct applications of these theorems later on.